Lecture 3, Forecasting, Section 1 and Part 3. In the previous part, we had the moving average method for stationary time series, and as you saw there, the moving average of n periods is the arithmetic average over the last n observations, right? So here we are going to have the second method for the stationary time series, which is exponential smoothing. And so in this method, the forecast, the current forecast, which will be for the next period, ft, will be a convex combination or a weighted average over the current observation, the current demand, and also the last forecast, which is ft minus 1. Okay, so as you see here, the alpha is the weight of the current demand, and 1 minus alpha is the weight of the last forecast, and alpha is a number between 0 to 1. So because of that, we can call this weighted average as a convex combination between the current demand and the last forecast for the current forecast. Okay, and by a simple rearrangement of the terms, we can obtain this. Ft will be equal to ft minus 1 minus alpha times et minus 1. So as you see here, the ft minus 1 is the last forecast, right? And et minus 1 is its error. So it's the error of the last forecast. So here somehow we are adjusting last forecast by its error to be the current forecast for the next period. Okay. So the exponential smoothing can be interpreted as this. The forecast in any period t is the forecast of the previous period t minus 1 minus some fraction of the observed forecast error in period t minus 1. Okay, so for example, if the forecast of t minus 1, the previous period, is too high, then we are going to decrease it to be adjusted for the forecast for the next period. Or if it's too low, then the error term will be a negative number, and then by having the minus alpha times the et minus 1, it will be a positive at the end. So we're going to increase the previous forecast to be adjusted for the current or the next period's forecast. Okay, let's have some analysis here to see how is the structure of the exponential smoothing. If we substitute the equal terms of the forecast in the equation of the exponential smoothing, and if we continue this in order to replace all the forecast values, then at the end we will have this. And as you see here, the forecast for period t will be a weighted average of the past observations, right? Yeah, as you see here, let's say observation of t minus I minus 1 has a weight which is ai here, and ai is alpha times 1 minus alpha to the power of I. Okay, and we also have this assumption here that sum over all the weights equals to 1. Okay, if we graph the weights over time, we see that this exponential smoothing is a kind of weighted moving average method that assigns a declining set of weights on all past data. So the most recent observations has higher weight, and the old observations have lower weight. Okay, the weights, which is alpha times 1 minus alpha to the power of I, can be approximated by a continuous exponential curve, which is this, And this is the reason that why this method is called exponential smoothing method. Okay, so if we do a comparison between the exponential smoothing and moving average, in the moving average we consider the same weight over all the most recent data. I mean, on the n most recent data, they will have all same weight. But here in exponential smoothing, we are assigning higher weights to the most recent data, the most recent observations. Okay, so and also we can say alpha here in exponential smoothing is playing the same role of n. So how? If we consider a higher value for alpha, then this means that we are going to assign more weight on the recent data and less weight on the past data, right? And if we consider lower alpha, this means that we are going to consider more weight or higher weight on the past data. So by having that, if we consider a larger value for alpha, this means that we are considering, let's say, small number of periods, I mean smaller n. And if we consider a lower weight, I mean smaller value for alpha, this means that we are assigning higher weights for the past data. So this means that we are expanding the range of the most recent data. I mean n increases, right? So yeah, by this essence we can say alpha here is playing the same role of n in moving average. If we consider a larger value for alpha, this means that we are going to assign higher weight to the most recent data, to the most recent observations. And this will increase the volatility of the forecast over time, because we are assigning higher weight to the most recent data. But if we decrease alpha and consider smaller value for alpha, this means that we are assigning higher weight on the past data, and it will generate more stable forecast for the future. And you can see this in this figure. Let me show with different colors. The yellow one now is the actual demand observation, okay, and let's say the green one here is the forecast of exponential smoothing with alpha of 0.4, and the blue one, this is the forecast of exponential smoothing with alpha of 0.1. And as you see here, the blue one is more stable than the green one. So yeah, that's why we say that. And usually in operations planning in the manufacturing environment, they usually consider a smaller value for alpha because they want to have more stable production plan for the future, rather than having more fluctuating actually plan. Okay. So let's have example here. Let's have the equation here for exponential smoothing. Ft equals alpha times d t minus 1 plus 1 minus alpha times ft minus 1. Okay, and here we assume that alpha equals 0.1. Okay, so as you see here, if you want to start from the first period, so what will be the ft minus 1, right? So here we assume that for the first period, the value of the forecast is the same as the observation. Okay, so by having that, now if we assume that we are at time t minus 1, which is let's say here t1, and we want to provide a forecast for the next period, which will be for quarter 2, then we will consider these two values, right? These two values in order to calculate the forecast. So the observed value, the observed value will be multiplied by 0.1, and the forecasted value will be multiplied by 0.9, and then we add up these two values. So we have the forecast for the next period. If we go ahead, then if we are here and we want to, I mean, in the second quarter, then these two values will be used to obtain the forecast value of the next period, and so on. Okay. So as you saw in our example in exponential smoothing, we require the previous forecast at each stage. So how can we start this method from the early stages? So yeah, as you saw in our example, we can assume that the forecast value of the first period is the same as the initial demand. I mean that initial period's demand. Okay, and and this assumption will have a large effect on the early forecast. So yeah, and so because of that, usually we consider a number of periods as the learning period. So, and after that, the impact of this assumption will be declined, so we can increase the accuracy of the forecast. So yeah, if we consider a number of periods as the learning period, then we can take, let's say, a simple average, I mean the arithmetic average for those periods, and then that average will be considered as the forecast instead of assuming the same value of the observed value for that period. So yeah, this is another approach here, and usually we do this. Usually we consider a number of periods from the data set for the learning, and then the rest will be used for let's say the test. Okay. So now let's see how the exponential smoothing and the moving average are consistent. So to do so, we define the average age of data. Okay, the average age of data. So in the moving average, we are assigning a same weight of 1 over n to all n past data. Okay, so if we multiply this same weight on the age of each observation, then at the end we can obtain the average age, which is this. So that then it will be n plus 1 divided by 2. Okay, and if we do the same for the exponential smoothing, then the average age will be 1 over alpha. Okay. Now, if we equate the average age of both methods by this, then we'll have this relationship between alpha and n. So for the moving average and exponential smoothing, if we obtain the alpha and n by this relationship, then we can say the results of both methods will be consistent. And what do we mean here by consistency between these two methods? We mean that we'll have same distribution of the errors obtained by these two methods if n and alpha have this relationship. Okay. So let's compare the two methods of exponential smoothing and moving average. The similarities, both methods are used in case of stationary demand process, but it doesn't mean that the demand or the series is stationary forever. So by adjusting the n and alpha, actually we can adjust our response to the shifts on demand in the future. And both methods are dependent on a single parameter. So moving average is dependent on n, and exponential smoothing is dependent on alpha. Okay, and both methods will lag behind the trend if exists. Yeah, these two methods are just appropriate for a stationary time series, not for trend time series. And if alpha equals 2 over n plus 1, this means that both methods will have same forecast error distribution and roughly same accuracy, but this doesn't mean that these two methods will have same forecast. Yeah. And for differences, ES exponential smoothing considers all past data, while MA just considers the last n data. So if we have an outlier in the series, that will be washed out after n periods in moving average, but it will stay in exponential smoothing forever. Yeah. And the MA moving average needs all n data to be saved in our, let's say, algorithm, in our application for computation. But in the ES, we just need to save the last forecast. So yeah, these are the similarities and differences between moving average and exponential smoothing. Okay.